I just made a Shiny app with binary logistic regression model as its backend. And I also just presented um, the app to a non-technical manager. So, so overview of this presentation would be two parts. First, just a little introduction to binary logistic regression. And second, I will give a demo of this um, a Shiny app named Diabetes app with binary logistic regression as its backend, and try to help with the non-technical manager to understand what it is of the um, logistical regression and how useful it is. So basically, to understand the logistic regression on the right-hand side here, the best way I would say is to understand, to get to know the linear regression first, because there are all the regressions techniques, but linear regression would be the mother of all the models. So yeah, so if you focus on the left-hand side, um, so this is a linear regression. So what is the linear regression does is um, it will try to so basically you've got let's say you've got a bunch of data points. Let's say the immigration department got a few applicants records for so these applicants trying to submit the immigration application. So in that scenario, okay. So for each applicant, you can see they just click the data of the applicant's body mass and the x-axis and their corresponding um, um, body size, right? So then there are a bunch of dots, red dots here representing the applicant's data. So what is the linear regression does is trying to fit a straight line across this the dot clouds, right? But there are different ways to fit the straight line. As you can see, the dashed line here, you could find multiple lines. That what linear regression model does is trying to find the best fit line across this dot cloud. So what is how do you define the best? Well, um, it is a little bit complicated. They use the different algorithm, mathematical algorithm, to pinpoint this best fit line. You could use the least squares. This is one algorithm. The other algorithm would be like maximum likelihood. So it's way too much complicated to explain here. So basically, what those linear squares, this which is a traditional statistical way to fit the line, is to minimize these sum of squares of this distance between the dots and the black line or any line, right? So basically, you are trying to find the line, and the line and the sort of distance of these dots or between the dots and the line, and you sum square of all those difference um, of the distance, right, between the dots and the line. So you get a number, but obviously different lines got different sum of squares of this distance. So the task of linear least square is just to find the find the just trying to minimize this quantity. Then you got the best fit line. Okay. Um, So let's focus on, yeah, if you understand this linear regression, let's focus on the right-hand side, which is logistic regression. Logistic regression is do the similar thing. Instead of fitting straight line across the dots, you just trying to fit the best fit S curve. So there you could draw different S curve, right? Um, Instead of this black dots, the black dots would be the best fit S curve to this data points. But the difference is that the data points here is different um, between the linear regression and logistic regression. The linear regression in the Y scale, right? In the Y scale, it's unlimited. Basically, it's continuous. It's numeric. But um, but in the for the logistic regression, the y-axis still continuous, but usually we want to stay in the scale from 0 to 1. And there are two categories because when you just taking the cutoff points at 0.5, you just basically you can consider this continuous scale into binary scale. So everything larger than 0.5, it would be diabetic, right? Everything is less than 0.5, it would be healthy. So basically, these all these dots still represent each applicant of the immigration. Um, but we know these dots. Okay, some of them are a healthy person, some of them are in diabetic person, right? So so basically, the similar thing happen. You are trying to find the best S curve, right? Instead of a straight line, you trying to find the best S curve. How do you find the best fit S curve? Well, it's still again, it's a little bit complicated. Basically, you are trying the fitting is not happening in this probability space from 0 to 1. Basically, it's happen in the what is called is log odd scale space. So in the log odd space, then you just basically you trying to fit a straight line there, and then you project back to this um, in this probability scale, right? So this is how the logistic regression trying to find the best fit line. By the way, it's still best fit S curve. By the way, it is still using algorithm named um, maximum likelihood. Okay, so the magic happens is that the usefulness of this is that um, once you find this um, best fit curve or best fit line, once there is a new applicant, let's say new applicant's body mass is like 100. So you just intercept with just plot this vertical line and intercept with S curve, S-shaped curve, then you got a probability. So for 100 body mass, obviously, you probably got very high probability of diabetic, right? So this is how um, and for any if you got a much less weight, so let's say it's like a 10 kilo, it's like a kid, so and you still intercept uh, draw a vertical line and intercept with S curve, so probabilities of diabetic is quite low, right? It's approaching zero. So in that case, well, it would be healthy. So that's how either linear regression or in this case, logistic regression make predictions to the new applicants or new data. All right. So let's move on. So to showcase, we are just using a diabetic data sets from M Air Bench R package. So it's public. So this um, this data sets originally contain, you can see like 768 records. Some of them are diabetic, some of them are not. So you can see positive and negative shows diabetic positive, diabetic negative, which is healthy. And there are other columns of data like age, pedigree, body mass. You can see body mass here, and pressure, glucose, pregnant or not. Oh, sorry, pregnant means how many children the applicant, if it is female, giving birth to. Um, so basically, I um, just clean this data a little bit. So you can see I just trying to very rough cleaning procedure, just remove any missing values presented in each columns. Then I just got a like a 392 rows or data sets, overall data sets that will be used for building our binary logistic regression model. So for this 392 rows, I just plot some, correlation between those variables, between any of those two variables, and the variables between diabetic. Also, you can see the distribution of um, negative and positive cases. Obviously, in this data set, we can see it's a little bit unbalanced. Yeah, that does not matter too much in this case. Let's move on. So in the first place, I just try to build a binary logistic regression single predictor. I just trying to use the mass as an independent predictor, and the model is like this. So I just trying to model the log odds of diabetes against the mass. So the mass only, which is only a predictor variable. And then and basically the red S curve, you can see that is a model being trained. And you can see that from this graph, you can see the model is not very good because you can see there's a lot of overlapped case of healthy case and diabetic case. Okay, so then I just progressively add the independent variables from glucose, pregnancy, and so basically I just build a full model here. The full model means I use every predicted variables available to model um, the log odds of diabetes. I use GRM, generalized linear models to do the modeling, and basically this is some model outputs. As you can see, these are coefficients. But basically, these are coefficients of each predicted variables. For example, the glucose is got a 1.2. But just beware that the coefficients here you can see is just in the log of space. So in order to make it useful, we have to transform into the into the odds ratio. Okay, so you can see for each independent variables, we got this coefficients. Basically, you can see that. Let's take glucose as an example. Basically, what it says is that for each unit increase of glucose here, for example, 1.2, if this glucose increased by 1 unit with 2.2, then in this odds ratio, the this so with the glucose variable, there will be more than 3 times more likely to get diabetes for this testing records than without the glucose variable presence. Well, it's quite a mouthful. It's basically this information tells you the variable importance. The bigger the odds ratios are, the more importance of these variables. Of course, there are other statistics like standard error or z value and the p value and z score. So basically, this tell us the if it's significant or not. And for example, for glucose, this is significant, right? There are other insignificant independent variables. But this is just the information I can tell you. And let's move on to have a look at the Shining app. Oh, okay. So this is before showing you the Shining app, and so this is talking about the variable importance. Basically, it's coming from the odds ratio. You can see that the glucose, remember, is 3.3. It's highest if you're looking at the highest is glucose in terms of coefficient. And the second would be pedigree, and then the mass. So that's why you can see the variable importance is basically is matched the order of the variable importance. You can see glucose, pedigree, and mass, and etc. So um, so this is so basically this is a Shining app. And just talking about. So basically, there are 3 tabs. Basically, there are 3 tabs. For this tab, model prediction, basically we set threshold as 0.5 because the probability is of diabetes is from 0 to 1. So the output of binary logistic regression model is given a probability output for each input, for each new case. For example, as this setting, so basically this numeric or numeric, as this setting, for example, glucose is 122 and pregnant 3 children. So as this setting, we will predict the probability of diabetic is 25%, which is below the 0.5. So we would consider this the testing new records would be healthy. As I said, the glucose is most influential or most important input independent variables. So if we change those glucose values, you can see that the model prediction for this case and will be changed, right? Then you become diabetic because glucose increased and it's over 0.5, so that's why it's predicted as diabetic. Of course, this is for the. Of course, you can change other variables. Let's just put back to the 122, and you remember that the second second influential variable would be I think is pedigree. So we just increase pedigree. You can see the pedigree can also be very influential, as very sensitive, and it can change the outcome of prediction as well. But the others like for example, the insulin, it will be not that as sensitive as the other two, as you can see. Although the chance is a little bit fluctuated, it's not linear. That's funny. But the pregnant, it seems it's like a linear, um, correlated with the outcome. But anyway, this is for the for one predicting case. But the model diagnostic panel just show you the overall performance of the model, basically predicting the records, new records in batch. In this case, remember we have 392 case overall. We used like 292 as the training case, but for the testing case, we just setting aside 99 case. So as you can see here, among the 99 case, we have 33. We have 33 as we have 33 as um, the observed positive case, which is diabetic, and 66 as negative case, which is healthy person. And as you can see, for each threshold, we at moments is 0.5, right? We just predict for each of these 99 cases, and then we got this confusion matrix. Basically, what it tells you that, for example, this value is true positive, which means there are 21 is observed positive, but the model predicts 21 as positive as well. So this is a true positive case. And this is true negative, which means there are 54 negative case among 66 observed case, but the model predicts 54 as true negative case. And here is false positive. Basically, what it is means is that there are 12 true negative case, which is observed, but model just predict 12 as positive. So that's why it is false positive. And here is false negative. Well, the same as they said, is that there is a 12 as positive observed, but the model predicts as negative, right? So that is why it's called false negative. But as you can see here, this is the case, these numbers only valid when threshold is sitting at 0.5. But when I change the threshold, let's say 0.8, from 0.5 to 0.8, so you can see all these numbers, false positive, false negative, true positive, all changed. Then, and you can see all the metrics are listed here, right? So once I change this threshold number, so everything would be changed. But here comes the question: how do we just really measure the model performance? Okay, the answer is the area under the ROC curve. So basically this part is under the curve. So this is a curve of this is a curve named ROC, and the area under this curve called the AUC, the area under the curve. So basically, we just there is a matrix named AUC. So everything under the curve, okay, under this curve, basically this part, then we will measure this. How much would be this in this area? The area, the maximum is 1, the minimum is, I would say, 0.5. Because 0.5 is like this, right? 0.5, 50%. Is this? So this is worst case. but the best case is one. So it's like a like curve like this. But the model here, so we basically we because once we vary the once we vary this threshold, we got a positive, we got positive, we got true positive and false positive. Well, basically, we just plot this true positive, okay, and false positive as a point. We basically join the dots and got this ROC curve, and then we calculate the area under this curve. And then in this case, we got a 82, about 82%. Of course, there's confidence intervals, but 82% um, over 100 is 100%, which is mean, which is the maximum. We got 82%, which is good. So this in this way, we should the model we built is good. There is this is this way we build the binary logistic regression model. So of course, this is a very simple way to build it. There's other more fancy ways, for example, automatically identify the um, best independent variables. Basically, what I'm trying to tell you is that you don't need to use all those. You don't really use all those input variables, but you can, you can use the selected one. But this process can be automatic, right? So this is what is called ultra machine learning. And of course, there are many variants of logistic regressions. For example, you could using regularizings like lasso. This is a more fancy algorithms to just prevent model. I mean, logistic agreement model is not overfitting your data. But this is beyond this scope of this introduction. Hopefully you enjoy this presentation, and thanks. Cheers.